Good afternoon to everybody. I'm Alfio Quarteroni. I have the pleasure to chair the plenary lecture given by Professor Alex Townsend. Alex was a brilliant undergraduate student at the University of Oxford, and then he graduated from the same university under the direction of Professor Nick Trefetton. This was in 2014. In 2016, he was appointed as assistant professor from Cornell University. Alex has been working on many different aspects of high-order methods, in particular spectral methods, on the conditioning of spectral matrices and how to improve the condition number of spectral matrices, on the transform methods based on special functions, on the solution of algebraic polynomial equations, and last but not least, on Chevron with two-dimensional functions. Chevron is one of the wonder kids of Professor Nick Trefetton, as everyone knows. Alex has been awarded several prizes, and let me just mention a couple of them. In 2003, he obtained the second Leslie Fox Prize. And in 2015, the first prize, the first Leslie Fox Prize on Hankel functions. Today, Alex will tell us about the spectral methods without discretization troubles or woes, right? And we are all eager to know how we can avoid that. Thanks a lot.
Thank you. What a wonderful conference. I've been having a great time. After the introduction of computers in the 1950s, problems began to be discretized so that they could be solved by machine. Nowadays, solving a science or engineering problem has essentially come to mean manipulating vectors and matrices, which the dimensions have been growing, of course, over the decades. Particularly when discretizing a differential equation, there's a whole multitude of choices that we must make, and many of these choices have been discussed this week, particularly in the high-order aspects. For example, what kind of continuum structures do you want to preserve at the discretization level? What discretization size is appropriate to resolve the solution? What kind of ways can we get fast linear algebra? My colleagues and I have been developing over the last 5 years a whole range of exploratory and adaptive algorithms and software systems to answer those questions for you in the global spectral methods community. So our aim is so that you can write down a problem and we will take care of the rest. We will decide the discretization size, how best to get fast linear algebra in there, and what kind of continuum structures we want to preserve. There's 3 main software systems that have come out of this. There are many others, this kind of thinking. The original one was Chevron that started in 2004. That's by far the biggest in the most lines of code, which may or may not be a good thing, to developers, to money, to fame. And there's also approximation, and there's Daedalus, which is, they're both relative newcomers on the block. And there's 3 main aspects that we focus on, which is good, robust numerical algorithms, because it's too hard for us to hide away discretizations from the user unless the algorithms behind the scenes are stable. We also almost always use adaptivity in both the discretization size as well as any algorithmic parameters. And we encapsulate, which is an object-oriented programming term to mean that we create objects that feel continuous, so you can be thinking about functions or differential operators, but behind the scenes, we are discretizing them so that you get numerical speed. And our goal is always to make you, as users, oblivious to the underlying discretizations. I thought I would start by just giving a highlight reel, things that I've enjoyed. on the 2D aspects, which is what my main focus has been on, we can now approximate functions on rectangles, on disks, on spheres, balls, cylinders, all simple geometries because we're using global spectral methods. We have a whole collection of several hundred commands for each different object there for you to do fast rotations, vector calculus decompositions. Maybe you want to do global optimization or root finding. We have these algorithms in there, and you can call them without ever needing to know about what's happening behind the scenes. We will choose how best to discretize the problem, the exact algorithms that we think your problem should be treated with. And so I've just collected some up here, for example. On the PDE side of things, there's, especially Daedalus, is a great package for solving partial differential equations in these simple geometries. Here is just a heat convection model simulation. It's actually a 3D model, which this is a 2D slice of. We also have been building up to more impressive PDEs, all on simple domains. So, for example, here's Navier-Stokes, which I just spoke about and explained how we do that behind the scenes. We also have simulations on the ball, and here's a simulation of a hemisphere, a droplet dancing, because it's being vibrated with music on its table. And these are all computed within either the Chevron 2 packages or the Daedalus packages at the top. And of course, this is what we're trying to get you to. We're trying to get people to be able to type in equations. We generate all the discretizations behind the scenes and deliver you back simulations. Now, of course, after you've calculated the solution to a PDE, you can go back to all the function commands that we have and explore the solution however you see fit. Okay, so I thought I would tell you the story about this. This kind of philosophy is really let's say, the brainchild of Nick Trefethen. It started in 2004, and it started with a less ambitious goal, which was just to become the continuous analog of MATLAB. So that was to be a system, an environment, where you could compute with functions as if they feel like you do with vectors and matrices already. So instead of sum of f, which in MATLAB just sums up the corresponding entries of the vector, it gave you back the continuous analog of that, which is the indefinite integration. Or diff of f was derivatives. In those early days, every function was represented by a Chebyshev expansion. We used to use value space for everything. Chebyshev points, Gauss-Legendre grids. Nowadays, we only ever use coefficients. And for almost every single command, 99.9% of the time, we're using coefficients, except when you give us the original function and we need to approximate it. The reason is because coefficients decay. And that gives us a really easy way to tell how many coefficients do we need to represent your function to machine precision. And here on the left, I'm using an algorithm we call CHOP, which is determining on the fly exactly how many coefficients are needed to represent that function to machine precision. Now, by eye, this seems obvious, but try to get a computer to robustly, reliably pick exactly where you should cut off. And we had a long time, maybe 10 years of experience in just picking which number, how many terms you should pick. Of course, here there's a plateau, which makes it a little bit more difficult. We can go further, and in the right mode in Chevron, you can get it to do automatically piecewise splitting blow-ups. It will automatically detect what kind of blow-up it is, where it is, exactly split to machine precision, where the discontinuity lies, and give you back a piecewise representation, which you then can compute with using all the other commands as if it was any other function. Once we got good at 1D functions, we also got very good at 1D differential equations, both linear and nonlinear BVPs, linear and nonlinear IVPs, systems. They're all done in an automatic way, so you don't have to care about the underlying discretization. I find this aspect of Chevron a perfect way to teach approximation theory or differential equations in an engineering class. And there's 2 good books that cover way more than I spoke about here. Okay, so after 2012, which is around about the time that I started getting involved, we had something on our mind, which was, can we take Chevron to another dimension, literally? Can we take it to 2 dimensions? And around that time, other packages started to appear. So based on the news from last night, with England losing, I thought I would keep the talk more jovial and summarize the last 5 years of our thinking, and my colleagues' thinking, with kind of 5 ideas that show you how we make algorithmic choices to hold up to our values of algorithms, encapsulation, and adaptivity. So idea 1, initially, we couldn't decide how to do 2D approximation. It seemed obvious to do tensor products, but when you do that, you have to rewrite a load of functions, and you have to care a lot about what happens in the 1D world. Here was an idea that allowed us to make code maintenance problems go away, and that was to leverage our 1D technology fully. And we did that by low-rank approximation, separating out variables. So as we all know, you can approximate a matrix by a low-rank representation, where R is some number less than or equal to its dimension. You can also do the same for functions and write them as products of 1D univariate functions, and a sum of those. It can be, low-rank approximation can be a more efficient representation, but usually not, as we found out. However, that's not the important thing. The important thing here is that we've split up the variables, and that if I want to do an operation like integration, differentiation, I can send it down to our very robust 1D code, and it can give me back the answer, and I don't need to know how it did that. So that if, as what happens regularly, we update the underlying algorithms, we automatically get that benefit in all the other systems, in all the other geometries. So how do we actually go about representing a function in low-rank approximation? Well, of course, the optimal way would be the continuous analog of the singular value decomposition. And we have that coded up in Chevron. It's an optimization. It's relatively expensive. We can't use that for on-the-fly calculations when you give us a function handle. So we use a technique that does not work in the discrete world when you have matrices, but works in the continuous world, which is we use Gaussian elimination, a particular variant of it, which is often called adaptive cross-approximation in the hierarchical matrices literature. What we do in the variant we have, what it does is it picks the maximum of the function, takes the corresponding column and row associated to it. That's a rank 1 function. It's a function of its column and row. We subtract it from the function, and we pick the global maximum again. And we repeat this process, slowly revealing the rank of the underlying function. And it is exactly Gaussian elimination written in an unusual way. It comes along in many different aspects, like 2-sided interpolative decomposition, skeleton decompositions. But we originally came to this field with Geddes-Newton, but probably there's only 2 people in the room that have heard of Geddes-Newton. So that's how we do function approximation. But of course, we don't pick out the global maximum. That would be too expensive. We make cheap approximations to it. And in the end, what you do is you represent your function as a bunch of slices, a bunch of column and row slices, often called a skeleton grid. And we found that it converges rapidly. We have some analysis to show that. It's not, it needs to be improved somewhat, but we don't know how. For example, here on the left, I'm showing how close Gaussian elimination matches the optimal SVD approximation. It's pretty much the same. We lose, not even a digit in terms of approximation power for each rank. And moreover, you might notice that the blue line goes below the red line. And that's because the blue line is more stable. Gaussian elimination happens, we find in practice, though we've not proven it, that Gaussian elimination is more stable than the SVD. Now, you can't use this for general matrices. This is because the functions are smooth. This is why this works. This is why that gap is so small. And if we have some analysis, for example, we know why it works because we don't pick the global maximum, we pick some cheap approximation to it, we understand why it's stable under those kind of mistakes. Okay, so because of that, we always gain a benefit. We can work on the 1D code, and it keeps helping us. Idea 2, we need fast algorithms, fast transforms, that convert us from values to coefficients and back fast. That is one of the most important aspects when you're doing adaptive computations, because we're going to keep asking the question over and over again, do we need to resolve? Do we need to chop? Do we need to grow our discretizations or shrink it? And we do that by going to between the nodal and modal bases. Right? We keep swapping back and forth when we're approximating a function. So much so that we're willing to give up a lot for fast transforms. For example, on the sphere, we could use spherical harmonics. And there is a fast transform there, but it's nowhere near FFT speed. So we went for the double Fourier sphere method, which is a method that allows us to continue to use double Fourier expansions on the sphere, and therefore FFTs. So let me just show you the basic idea is, let's take this atlas globe, write it in spherical coordinates. When you do that, you have lost some symmetry that must be imposed on the sphere. And you can add that back in by doubling up. It looks like this when you've doubled up. If I take the one jigsaw piece from the corner and I move it over and I flip, that's the symmetry. If I take this piece of corner over here and I flip, that's the symmetry. And so if I draw it out, it's like G, H, and then upside down H, upside down G. It's called footprint symmetry, or BMC symmetry. And this is the kind of symmetry now that we rigorously impose on the functions that come in to try to keep them regular on the sphere. Of course, we don't do tensor product grids with this, which is the standard disadvantage with double Fourier sphere, that you have clustering of your node set at the poles. So you've over-resolved the function at the poles precisely where it's probably near constant if it's smooth. We use our skeleton grids, which partially overcome that oversampling issue. Right? We apply Gaussian elimination in this doubled up BMC symmetry. We do it with 2x2 pivots just right so that the symmetry is never lost. It's always imposed. And in our system, we never double up. We just remember that the other side is there. Right? We virtually have it doubled up. So it's not even double the cost in that regard either. Now, Mikhail Savinsky, since we came up with this, has a much faster spherical harmonic transform, and I'm extremely excited by that. However, it's still not FFT speed. So in a highly adaptive software system, we still need our doubled up grids. Moreover, we've been developing a whole range of fast transforms because we are always asking that adaptivity question in various circumstances. And by now we have tons of transforms between different orthogonal polynomial spaces and different types of grids to answer those questions. Like the discrete Chebyshev transform is how we convert Chebyshev values to Chebyshev nodes to ask how long does a Chebyshev series need to be to resolve the solution. We're applying this on each slice of our 1D representations to ask the question, how many degrees do we need? And we also have non-uniform FFTs, which allow us to do some fast rotations, for example. Now, unlike many fast transforms in the literature, these are all based on FFTW. That's all they call. They essentially do very little and then call a bunch of FFTs, rather than some other approaches like oversampling, where you do a bit more work but then call one. The reason that we need to use FFTW is because really it came out of the fact that we're in MATLAB. And we can't write these kind of codes. We need to call straight to C code, and that makes it a lot faster. Of course, this now individually tunes to your individual architecture, which makes it easier for us to maintain in the future. Okay, so before that's all about functions. But to get ourselves to differential equations, what we needed was an idea to make sure that we could discretize differential operators automatically without telling the user, like, what ingredients does this operator contain? And and have it be stable and fast linear algebra. And this is what this method is. Of course, we all know the spectral collocation method, which I'll just introduce. You take a second order finite difference grid. We all know it creates tridiagonal matrices. You can increase the order, and as you increase the order, increase the bandwidth. In the limit, in the spectral limit, you have spectral collocation, which is the high order limit of finite differences, or at least you can think about it like that. Of course, we don't use equally spaced grids because they're unstable. We use Chebyshev. And this has been a wonderful way to teach spectral methods to people. However, the matrices that come out of this are dense and ill-conditioned. And that makes it challenging, at least in the PDE world, where we're doing 2D computations, where everything here gets squared in terms of the condition number, and the matrices are often squared times larger, to do real computations based on an algorithm which is just a little bit unstable. So we had to come up with a new idea, and we know an idea that works. All of us know, and all the physicists know, what works in the periodic setting, and that's the Fourier spectral method. So the Fourier spectral method, I barely need to introduce it, just writes down an ansatz for the solution as a Fourier series and creates, typically, generically, banded matrices with maybe one dense row. And as you may not know about Fourier spectral methods is up to a diagonal scaling of the columns, it's perfectly well conditioned, assuming the variable coefficients. Let's say constant coefficient, to keep that precise. And what's more so is that all linear algebra, like Gaussian elimination and the QR, respects column scalings. It only passes information down rows. So column scaling does not affect the accuracy of any of those linear solves. So you don't even need to do the diagonal scaling in practice to get an accurate solution to a Fourier spectral method discretization. So Sheehan and I sat in a room and we asked ourselves basically the question, what is the non-periodic analog of Fourier? Right? Chebyshev is essentially the non-periodic analog of Fourier. Why is Fourier sparse? Because it has sparse differentiation recurrences. Right? There's one-to-one. So all we need to do is find sparse differentiation recurrences for Chebyshev. And you go on the digital mathematical library of functions, and you find a whole host, a dictionary, essentially, of sparse recurrences for derivatives. This means you can create a sparse spectral method in the non-periodic setting that has all the same properties. Of course, there is the extra catch that you've converted bases. And so you must need other recurrences that happen to also be sparse to take care of that fact. But the real advantage of this, there were plenty of other sparse spectral methods out there, but it's the fact that this one feels so much like the Fourier spectral method. That's what we desperately needed in an adaptive, encapsulated code. Because now we can build up differential equations based on ingredients, and we treat the Fourier the way identically, and have exactly the same properties. Almost banded matrices, banded plus except one row, and also well conditioning. And there's a whole load of techniques that are related, and every time I give a talk on the autospherical spectral method, I find out another one. So if you have one in mind, please send me an email. I'm trying to collect them up. Okay. Idea 4 was if we really want to be correct about things, we need to do some infinite dimensional algebra here, which means we're going to discretize a differential equation, and it's going to be an infinity by infinity matrix if we don't chop. And what we don't want to do is perturb that matrix in any way, particularly for a singly perturbed problem. We don't want to do a finite section of that matrix and solve the finite linear system, because that perturbs the matrix in the operator in hard-to-control ways. So we have, at least in approxfun particularly, very good implementation of adaptive QR algorithm, which solves the infinite linear system exactly under a perturbed right-hand side. So we carefully construct, using Gibbons rotations, a perturbation of the right-hand side of our infinite linear system, so the solution can be solved, is a polynomial, and can be solved by a finite system. So we basically compute all these Gibbons rotations, perturb a couple of entries of the right-hand side, to 0, make it exactly a polynomial, and then to ensure that the solution is exactly a polynomial too, and solve an underlying finite dimensional system that solves the infinite system exactly under a perturbation of the right-hand side. Just like that one there. What will the error be? We know it exactly before we've actually done the solve, which means we exactly know how to do adaptivity, because we know the error before we've calculated the solution. We know the backward error. This is related to many ideas, and really it's Lanchos who had the idea of perturbing the right-hand side so the solution was exactly a polynomial. And we've come up with an algorithm that constructs that perturbation. It means that the ultraspherical spectral method is surprisingly good at singly perturbed differential equations, and we don't understand why in all cases. Because it's related to the Fourier spectral method, and derivatives are essentially diagonal matrices, it's really good for high-order ODEs. Here I've chosen such a stupidly high-order ODE to demonstrate the issue, to demonstrate how good it actually is. And you can see here also that all the stuff here is encapsulated. We picked the n, we resolved, we threw it back to you. We could do piecewise splitting if you gave us the splitting, and so on. It's also good when you have generalized Navier-Stokes, which I gave a talk about earlier, because here is a problem that when I saw it, made me jump up and get excited, because here's a partial differential equation that has really high differential derivatives, is practical, at least to Smolak and Dunkel at MIT, and we can use the ultraspherical spectral method in different ways to get solutions for them on the disk and on the ball using the doubled up stuff. At every step of this, we're deciding, because they do massive runs, the adaptivity for them, because they do runs with lots of different algorithmic choices for gammas, different model choices for the gammas, and we adaptively select them when they do 1,000 runs so that we don't have to sit there by hand and figure out what discretization is necessary. Okay, idea 5 is we need expiratory algorithms. There's some problems out there like PDE solvers that we have in Chevron and approximation that select the algorithm of choice from an operator that comes in. You give us the operator as like a function handle. We know nothing more than how to evaluate it, how to apply it. And from that, we have to figure out what it's made of, how best to discretize it, and what solver to use at the end of the day, and what discretization size. And we go back to idea 1, and we try to repeat the same thinking of using our 1D knowledge, in this case the ultraspherical spectral method, to deliver us solutions to two-dimensional PDEs. And we use, again, a separable expansion of a PDE. Now, the average PDE with variable coefficients has an infinite expansion here. R needs to be infinity. But for most cases, for example, here I've just chosen Poisson with an extra term. This has a splitting rank, is what we say, which is infinity, mathematically. But of course, we're only going to ever do things to machine precision. So we can cut that expansion so it's accurate to machine precision, and 7 terms is enough to capture that. We compute these decompositions using tensor train decompositions. So it's similar in feeling to an SVD. It tells us way more than just R. It tells us the terms in the equation that dominate over the others. We basically order them in terms of which ones dominate and which ones don't. And we're hoping to use that in the future to tell us how to maybe split the PDE up. We can also read off from this nonlinear and linear parts. So what we do to understand linear and nonlinear parts is we pass it through, we do automatic differentiation, which means you think we're going to pass into the operator x, y, and u. We're not going to do that. We're going to pass in objects, x, y, and u, that have behind the scenes basically trackers that track where the evaluation tree goes. Every time an evaluation gets triggered, we build up basically an AD tree, which tells us both where the nonlinear parts are in your operator and where the linear parts are. It tells us, because of the tensor train decomposition, how to accurately split up the PDE into one-dimensional objects, which we can then feed in to our one-dimensional code and give us back matrices to discretize that PDE. So in the end of the end of the story is, at some level, we're going to solve some kind of discrete system. Now, we have adaptive QR solvers in some sense for these kind of problems, but I won't discuss it. But if we're just thinking of just solving it as a discrete problem, we then make choices based on what we found out to how we solve it. For example, in one of the easy cases, which is like r equals 2, we just have a Sylvester matrix equation with some boundary conditions under some constraint usually. And we can then feed it off to a bunch of different solvers to exploit structure that we've already found out from our tensor train decomposition. So, I mean, we find out if it's Poisson, if it's Helmholtz, if it's any kind of PDE that's dominated by the Laplacian, we can find that out and split it off if we deem that that's useful. And then we pass it to these algorithms, and then we get back the solution. Hopefully in the future, because we know so much about the PDE from feeding in these AD objects, we can automatically call code that splits off the nonlinear part, does IMEC schemes, and so on. And at the end, what you get is a whole range of software for solving problems on these geometries using as few bits of discrete knowledge as you need to get the job done. All these problems here were solved with the user feeding in some minimal lines of code, and we did the rest. Okay, I have one more bonus idea to finish here. Okay, for a long time, we've been trying to make the user oblivious to discretizations. And then recently, we started thinking, well, maybe we can make the algorithms themselves oblivious to the underlying discretization, which means that we can build algorithms that essentially deal with the continuous objects and then just feed in a Chevron or a Chevron2 discrete object that then goes through that symbolic algorithm and makes it a discrete one. But at no point do we have to figure out how best to discretize any kind of differential operator. So we're starting to use this for Krylov iterations on spectral methods, because for a long time it was difficult to know how to precondition a spectral method, particularly variable coefficients, which means none of our software right now can use iterative solvers robustly. And so we've been trying to get the algorithms to be at the continuous level so we can use operator preconditioning, which we know more about than some weird combination of the operator itself and its discretization, to try to get solvers that are discretization oblivious. Andrew Horning, who's in the audience somewhere, will be discussing this in the eigenvalue case, which we are now using as sort of a training exercise for ourselves to see how far we can push discretization oblivious algorithms. His algorithm essentially can work at the continuous level, but of course it's not practical. It's a symbolic algorithm. And then we feed into it functions that are discrete. That makes it a discrete practical algorithm. And it hopefully in the future will allow us to solve eigenvalue problems and do iterative methods without increasing the sensitivity of the eigenvalues from our underlying discretizations, without trying to figure out spaces that preserve the continuum structure. So Andrew's talk is in room 750 tomorrow. And I would like to just end with a beautiful line from the book Exploring ODEs, which is, and I'll paraphrase it, which is, what if all you had to do to solve a problem were just to write it down? We don't know, but it'll be a fun task to get there, and if it changes the world, so be it. Thank you.
Thank you very much for this very inspiring talk. Questions? Yes.
So I think there's one more bonus idea that you may have, and I'd like to get your thoughts on, is maybe number 7 is give your software away for free to everybody. And that's something that's a new innovation, moderately, and I'd like to just hear what you think about.
Right. Yeah. It's a double-edged sword. We both get criticized because we reveal our algorithms that do such generality, and then someone comes along and makes a specific task and does slightly better than our general algorithm. But it's also a huge benefit because, well, Randy Levesque has a fantastic essay on the reasons for open source software, of how we can build communities to collaborate, and how best it is to apply to different problem types. I know I can't really say too much because Chevron is in a proprietary language called MATLAB, which limits its open source feeling, though it is freely available and open source. Whereas in Python or in Julia, these are both open free movements that have a huge list of collaborators and contributors that use the software. So this is, of course, we both agree that we should always release software so that we can compare and learn from each other.
More questions?
So I had a question about is it number 4, the infinite dimensional linear algebra, which I think of as kind of a lazy evaluation of an infinite matrix problem. It's certainly beautiful, but how you made it sound as if it's definitely advantageous to do things that way. How solid is the case that you need to lazily evaluate the infinite problem rather than truncate the way most people have been doing so long in order to effectively solve these infinite matrix problems?
Well, it depends on the problem at hand. I think for singly perturbed problems, where perturbing the operator by a little bit can have massive consequences to the final solution, it's a tool to use. Of course, in Chevron, we do not use the infinite dimensional QR because it would require us to write our own, because it's not in LAPAC, for example, and that would slow the system down so much that the benefits that it brings don't outweigh the cost of calling each time. So we end up doing finite sections and doubling. It also is 2 times faster because it finds out the optimal n to truncate at the same time as doing the solve. Whereas in Chevron, we both solve and then we double and solve and double and solve and double, and there's more work being done there because every time you recall the algorithm, we start fresh.
So for the one-dimensional case, it is very easy to do multi-elements, right? With we have discontinuity and stuff like that. In the 2-dimensional case, have you ever considered to adaptively using multi-elements?
I was going to put that in my slides, but so I had a high school student, one of the best high school students in the country, in the US, worked with me for 2 years. He won $175,000. Okay? He won a national competition, and he wrote an adaptive spectral element solver based on the ultraspherical spectral method that had different features than what you would usually think of because it was creating sparse matrices. And particularly because of the singly perturbed, the fact that the ultraspherical method can solve singly perturbed problems accurately, it was good for problems where the mesh was collapsing and creating skinny elements. So I have been thinking about it. I'm trying to push myself in that direction, but I only have this thing that works on skinny triangles.
The real world has data with outliers and everything. What's the vision going forward? Is it to somebody else does with reprocessing of the data and then it gets put into this framework? Or is there some vision to put the fact that data is unclean into that framework?
We don't have a vision for that. We've always been thinking, I'm being honest, we've always been thinking about, I would say, clean, problems on simple geometries. But it would be interesting to know how we can use our globally accurate, like spectrally accurate methods in a setting where there's noise. Yeah, thank you.
If you have coefficients in your partial differential equations, you use this approximation based on, say, separating the variables for the coefficients and truncating, and how this affect the overall accuracy of the scheme.
Well, we only ever truncate away things below machine precision. So up to machine precision, we truncate the variable coefficients to polynomials, but that truncation is good to 16 digits of accuracy.
How do you know that?
Well, on the variable coefficients, we truncate them to 16 digits of accuracy. Is your question, how does that affect the global solution?
Well, first of all, how do you know that you are below the 16-digit accuracy when you truncate?
Because when we feed it into our AD, when we get the AD tree, it actually builds up, we basically find out all the objects that the differential equation is made of. So and we find out what the variable equation is as a function. And we can call our 2D adaptive code to find out exactly how to resolve the variable coefficients. So we know them exactly because of the AD tree. Of course, for a singly perturbed partial differential equation or one that's very sensitive to perturbations, there may be issues there with the accuracy of the final solution if we perturb the operator just by a little bit. And we haven't thought about those situations.
And if you have, say, non-symmetric operators, you have skew symmetric, say, transport terms that are skewed to the grid.
Yep.
When you use this orthogonal decomposition, how are you going to handle it? Do you need to stabilize? Do you need to do something special?
So on all the time-dependent, like the Navier-Stokes and things, we're always adding filtering in. We're adding regularity into the thing to try to keep the function stable. But this is a problem. This is a problem going forward for adaptive codes. How do we automatically detect the kind of symmetries and conservation laws that we want to preserve and implement them without the user telling us precisely what these are?
So what is your thinking about, because you have this now banded system with your coefficients, the matrix is banded.
Yeah.
And if you treat time as another space variable, and then you want to solve everything truly in space-time, so basically in time, also you have the banded system. So you don't have to worry, like what you mentioned about, using linear multi-step methods. So everything, space and time, solved as a giant system of Chebyshev. So
Right.
do you have any plan for that for the future?
Well, like spectral in time. That's what we. Yeah.
Space-time.
Space-time. Yeah. We need to sit down and think, because how do we get from the given operator, which is what we're trying to achieve here, to get it to a situation where we know exactly what to preserve? That's the task at hand. We don't want to go away and give up the fact that we're trying to do encapsulation here, because that's what's driving us forward. Otherwise, we end up just becoming for particular PDEs. Right? So I don't have many thoughts on it, but this is something that if we were going to push to the space-time, we need to get right.
In your estimate, when you use your Gaussian elimination, the surrogate for the SVD, say, you show an estimate where you have this optimal behavior with respect to rho, and you have rho to the power minus r. You have any way to compute, to estimate a constant? Or does it depend on r?
We do not do that. We wouldn't do, so this is the question that you have the Gaussian elimination scheme, you know an error estimate, like how it converges, but how do you compute that rate? That's not the kind of questions that we ask. Because the algorithm is greedy, we select those pivots in Gaussian elimination and greedily decide when to stop. Of course, that estimate
on the basis of which criteria?
Sorry?
Which criteria are you using to decide when to stop?
When the pivots normalize with respect to the size of the two slices, goes below machine precision, plus a bunch of chopping algorithms that are engineering that we've been deciding for the last 10 years. Okay.
Good. Any more questions? If not, let us thank our speaker again.